Hello everyone, I'm Jaegol Chu, one of the instructors of this course. So this is already 15th week and we continue studying deep learning, focusing on attention model. So the objectives of this week's lecture is to understand how this attention model works, and then its mainstream applications such as image captioning and machine translation. So what is the problem of image captioning? Given a particular image, and then image captioning will generate some sentences or phrases that explains this given images as free text form. In order to perform this task of image captioning using a deep learning model, given a particular image, we can utilize some representative convolutional neural network models that can classify this image into, for example, one of 1,000 categories in ImageNet dataset. So in this case, internally our deep learning model can be designed in this form. So we go through a sequence of convolutional layers and then the max pooling, and then another set of convolutional layers and the max pooling and so on. And at the final stage, we just concatenate all the activation maps into a single vertical vectors, and then we start with some fully connected layers, such as fully connected layers of these three steps. And then finally, depending on the number of classes that we want to classify, we can perform the softmax layer, which classifies one of those given categories. So in this case, this deep learning model can be viewed as extracting some useful and meaningful information internally in this process. And so we utilize this model as a step of extracting out some useful information from our image for our own image captioning task. And then, because this model is originally designed for classifying this image into maybe 1,000 different classes, and so we throw out some of the last layers, because this task of classifying this image into one of 1,000 classes is not our own purpose. But internally, somewhere in the middle, it should have capture some meaningful information, and then we actually utilize such a meaningful information that was extracted out from some of this internal features. So for example, we can bring those feature vector that was generated as an output at this fully connected layer that generates this 4096 dimensional vector. And then using this feature vector representation that can contain some useful information from our image, and then we utilize this vector as the hidden state vector from the previous time step in our RNN module. So by using this RNN module, we generate a sequence of caption words that explains our test image, and initially as an input word, we can give a start of string or start of sentence type of token or word input word here. And then given this hidden state vector from the previous time step as this feature vector of our image, and then using this input word vector that is in this case a start of string token vector, and then they are further transformed by using this linear transformation, and then further transformed by our nonlinear unit of this 10h function. And that way we can generate the hidden state vector at the current time step, and then it will finally be used to generate the first word that is starting with our image caption for the corresponding image. And then the rest of the process will be exactly the same as just the typical language generation model by using the RNN. So in other words, by using the previous time steps hidden vector, and then by using this input word that was generated in the previous time step. And then we will generate another word that will be placed in the next time step, and so on. So until we find some special character that indicates the end of this string of this image caption, that's when we stop this generation process. And that way we can finish writing the caption sentence or phrase for this given image. So that is the overall process for this image caption by using the deep learning model. And let's look at some example of this image captioning by using this deep learning model. So given these images, these are the machine generated caption words, and they mostly make sense. But sometimes our image captioning model didn't generate well about the correct captions. So for example, in this case, it generated this caption of a woman is holding a cat in her hand, and probably our model was confused due to this hairy kind of stuffs or material found in our image, and then that's why it was confused. It was a cat. So these caption result, although they are not exactly correct, but they are making much sense. So that can show that our image captioning model based on our deep learning is understanding some of these semantics underlying in our image in order to generate this caption phrases or sentences. Up to this point, although we studied an interesting deep learning model that effectively combines this CNN with an RNN, but there was no notion of this attention. But in order to improve this task of image captioning, we can introduce additional module called attention. So this is an overview of our attention. Attention-based image captioning model. So given an image, we extract out some useful features by using this convolutional neural net module. And then when generating our captions, we use RNN-based model, but in this RNN, there is an additional module called this attention. Let me just go through again this image captioning process that we just learned. So given this image that has this height and width and the depth of 3, which corresponds to RGB, and then by using a CNN, we extracted out some meaningful features. And then it worked as a hidden state vector in the previous time step, and it started to generate those caption words. So that was the model that we studied in the previous slides. But in this model, when our RNN module sees this image information, and then this RNN looks at this whole image only once in the very beginning of our caption generation processes. But what if RNN looks at different parts of the image at each of our time steps when generating different words? So let's look at the image captioning model by using the attention module. So given this input image, we go through this CNN model, and then previously we extracted out some feature vector from the fully connected layer. So in that case, that high dimensional vector extracted out from this fully connected layer will not contain any kind of spatial information. But let's consider is extracting out some feature map from a particular convolutional layer. So at some convolutional layer, suppose the activation map size was, for example, 14 by 14, and then the depth was 256. So in this case, the meaning of this is that we extracted out 256 dimensional feature vectors at every different location. So we can think of this kind of 14 by 14 grid of images that corresponds to each of these different locations that was divided by 14 by 14 regions in our image. And then for each region, we can consider this vertical vector contains the useful feature vector information that is represented by this 256 dimensional vector. And this is represented as this rectangle. And then here, this L is corresponding to different locations. So we have this many different locations, which is in total 196 different locations. And then at each locations, we extracted out 256 different feature information. And that is the starting point when initiating our RNN process to generate our captioning model. And then it kind of works as the initial hidden state vector coming from the previous time step. And then when generating the output, instead of generating just output word, we actually generate some distribution vector over L different locations. And the distribution means when considering this A1, and this A1 will have the same size of 14 by 14 region. So in total, we will have 196 different values, and then the summation of all these values will be 1. So that way, we can view this 14 by 14 matrix as a distribution over different region. And this distribution works as the weighting factor that indicates where to look more closely at in our feature map extracted from our convolutional neural net. So let's just simplify our activation map by maybe 3 by 3. And then we will have some depths as maybe 256. And then suppose this A1 was 0.1 and 0 and 0.2 and 0.1 and then 0.1 and then 0.5 and 0, 0, 0. So in this case, it indicates that we have to look at this part, which corresponds to this region with the probability of 50%. And then at the same time, we have to look at this part with the 0 probability, which means we have to ignore that part at this moment, and then 20% on this part, and so on. Okay? And then these values will be multiplied with each of our feature vector that has this 256 dimensional vector. Okay? And then after multiplying this weighting vector that can be viewed as some kind of distribution over L different locations with each of these feature vectors. And then we can compute the weighted sum of these feature vectors where the weight is corresponding to these probabilities. And then altogether, we will obtain one single feature vector that has the dimension of 256, because each of these 256 dimensions were added with their own weight to generate one single 256 dimensional feature vector. And that will work as the additional input to our RNN module. So in this case, in our RNN module, it will take the input as this weighted feature vector, and then the first word, which can be just a start of string or start of token. Okay, so now our RNN module will take an input as this weighted feature vector, and then this previous time steps word as an input. And again, this feature vector can be viewed as the feature vector that considers more on a particular region that we have to focus more on to generate the current time steps word vector. So yeah, when going through this RNN, and then finally we will generate our word that should appear in the current time step, and then now we generate another distribution over L different regions. Okay, and then again, if we had 3 by 3 regions of this feature map, and then this one will also have the same size of this 3 by 3 distribution vector or matrix, and then it will now generate a different distribution from this guy, and then the high weight will be placed, for example, corresponding to the region that should be focused more on to generate the next word. And then this new attention map or this distribution matrix will be applied to this feature map to generate the next time steps weighted feature vector. And then this one will generate the next word, and then another distribution over L different regions to look at in order to generate the next time steps word. So this is called the attention mechanism. So at each time we generated this distribution over L different location, and this one works as the indicator about where to look at in order to generate the next word. And that can be viewed as some kind of attention that we give to a particular region of our image when generating a particular word. And this attention weighted feature vector is often called a context vector. Okay, so this is how this attention model works. And then let's look at this example. And given this image, suppose this one was a machine generated caption. And then, there are two different models called the soft attention and the hard attention, but let's ignore the difference between these two. But these two are just a different attention model with a little bit of minor detailed differences. But when looking at each of these words, when generating, for example, this word of bird, and then it properly gives an attention to the relevant part of our image, which is the region that contains this word, this bird in our image. And then, for example, when generating the word of water, then it properly looks at this region of this background part, which is covered by our water or sea. Okay, so that way we can think of our machine as looking at different part to generate a different word, and then this one is quite similar to how humans are generating these captions by focusing on different part at different time. And let's look at some other example. So given this image, this is the generated caption, and then when generating this word frisbee, and then it properly looks at this region of image that contains this object of frisbee, and then dog is standing on a hardwood floor. When generating this word of dog, and then this is the corresponding attention. Now let's look at a slightly different problem called a visual question answering compared to this image captioning problem. So in this visual question answering, or in short VQA task, we are given this input image, and also additionally we are given this question that is described as our natural language sentence. And then our deep learning model should generate a particular word as also the form of a natural language form. And this answer is a proper answer for this corresponding question and this image. And this is called the visual question answering task. And let's look at the example. So in this figure, so this was the question: what endangered animal is featured on the truck? And in this case, the answer is this bald eagle. And let's look at some other example as well. And then these are the visual question answering examples. And by using those data with the question and the corresponding image and also the correct answers, we can train our deep learning model. This deep learning model, to solve this visual question answering, can be also built by using RNNs with this attention module. So in this case, we start with this image and then extract out some meaningful feature from this image by using this convolutional neural net. And then we extract out some feature map such as this. And then it can be viewed as having the feature map of 3 by 4, which divides our image into this 3 by 4 grid. And then you can think of some feature map that has a particular dimension. So for example, the dimension will be 256. And then at each different time step, instead of generating directly the sequence of caption words, we now think of the RNN module that keeps taking the input as these question word sequences. And in this case, we can also generate some attention map, just like the image captioning task. But in this case, we do not generate word output in this case, because we are just trying to understand what these questions means. And so given this attention map or this distribution over this 3 by 4 different regions, and then we can still compute this context vector or weighted average vector of this each of these 256 dimensional vector. And then we feed this attention weighted vectors or context vectors at each different time step by using a different weight vector or attention vector. And that way, at the end, we can view the output vector as the meaningful vector that contains the information extracted from this question and this image. And then finally, by using this meaningful feature vector that is an output from our RNN module as a result of an understanding this question and image, and then at the end we extract out some meaningful feature vectors from our CNN module by using the same image, and then we go through some typical neural network in order to obtain the answer. So in this case, suppose our answer is one single word among maybe 500 different vocabulary words. And in this case, the task will be to pick up one word out of this 500 different vocabulary words. And that way, we can form this softmax layer at the end in order to choose the correct word answer. So in this case, the key part is this part. So we have to understand this question, and then by going through each of these words in our question, we have to extract out some meaningful information from the corresponding regions in our image. So that way at the end we should be able to extract out some meaningful feature vector in order to obtain the final answer for a particular word. And these are the example of this attention module output. And then in this case the final attention module output will be highlighted or assigned high weights on this particular region in our image that is relevant to our answer for this particular question. And also in this case, when generating this proper answer of word cake, and then at the end of this RNN sequences, the output for this attention module will be focusing on this relevant part for our answer word. Again, in this model, at the end of the output of this RNN module, you can view this final output as the attention map that corresponds to this, and then when combining this CNN extracted feature map, it can be viewed as just a weighted sum operations, just like the process of generating a context vector. Okay? By using such a context vector, we can generate a particular word for our correct answer. Now let's turn to a slightly different model called a sequence to sequence. So in this model, unlike the image captioning model, where we take the input as an image and then generate a sequence of words, but here in this case, we also take the input as a sequence. So in this case, it's found in many natural language tasks such as chatbot and machine translations and so on. So in this chatbot or email auto response systems, suppose you are given this input as a kind of question, and then given this question we have to generate a sequence of response words. And in this case, unlike the CNN module that extract out some meaningful feature vector from our image, we can extract out some meaningful feature vector by using this RNN module that takes the input as the sequence of these input words. And then at the end, the final hidden state vector will contain some useful information extracted from our question here. And then this hidden state vector will work as the previous time steps hidden state vector when generating now these sequence of an output words. So even though they are composed of these two different RNN modules, we can view them as composed of encoding module and also decoding module, where encoder part will extract out some meaningful information coming from these input sentences. And then in the decoding phase, it will start to generate these output words based on these extracted feature vector from this encoding stage. We can use this sequence to sequence model for machine translation tasks. So in this case, the training data is a pair of a sentence written in one language and then its corresponding sentence written in another target language. And then in this case, by using this sentence in a source language, we go through this encoding stage in our RNN module. And then at the end of our time step, we extract out some hidden state vector, and then it will work as the initial hidden state vector for our decoding stage. And then we will generate each of these words that will form our machine translated output in a target language. So in this case, this guy is corresponding to a start of token or a sentence, and then it will generate the first word, and then this one will be fed as an input word in the next time step in our decoder RNN module. So that way we can exactly apply this sequence to sequence model for this machine translation task by designing our training data as a pair of this source sentence and this machine translated target sentence. So in this sequence to sequence module, there was no notion of an attention. So the same problem persists in the case of an image captioning. So in this case, this vector should contain all the information that was found in our source sentence. And then in the decoding phase, we only look at this entire input sentence only once at the very beginning of this generation phase. But in this machine translation processes, we may have to look at a different part of the source images to generate the corresponding word in the target sentence. So that way we can apply this attention module in this sequence to sequence mechanism. So in this case, when this performing this encoding phase, we do not just use the hidden state vector at the last step, but we actually utilize the hidden state vector that was generated at every different time step in this input sequence of words. And then in the decoding phase is exactly the same as the image captioning phase. So starting with this null or start of sequence character, and then we first generate some attention map that has, in this case, we have 5 different hidden state vectors, and then now our attention vector or the distribution over these different encoding vector should have the same dimension of 5, and then this one is a sum to 1 and a non-negative vector that can be viewed as the distribution over this encoding sequence. So we apply this weights in order to compute this weighted sum of these encoding vectors, and then generate this attention weighted context vector, and then that will be given as an additional input to our RNN module. So that is represented by this additional arrow, and then we generate the corresponding word, and then also we generate another attention vector, and then we apply it to the same set of encoding hidden state vectors, and then generate differently weighted context vector, and then that will be also given to the input, given as the input to the RNN in the next time step. So that way we can generate those machine translation outputs word by word by assigning different attention or weight vectors to this encoding state, hidden state vectors. For more example, you can look at this website, which is a Google's official TensorFlow-based implementation for this sequence-to-sequence model with an attention. And then given these source sentence, it will generate this output, but when generating each of these output words, it will have a different attention vectors. Now let's look at this attention example. So suppose we have this source sentence, and then these are machine generated target sentence, and we can have the encoding hidden state vector for each of these words in our source sentence, and then when generating each of our word in the target sentence, and then it will have its own attention vector that is applied to these encoding vectors, and then each row can be viewed as an attention vector when used when generating each of these output words. So in this case, we can view that when generating these output words, it follows a sequence of this source sentences. So it means we scan through each of these words in the source sentence and then generate its corresponding word in the target language. But sometimes it actually changes the order of translating these word level sequences. So in this case, instead of looking at this guy first and then next and then next, we actually looked at this word first to generate this word, and then we actually followed the reverse order in order to properly generate the target sentences in different languages. So that way, we can view that this attention-based sequence-to-sequence model for machine translation was able to properly learn the correct sequence or orders for the different languages' grammars. So these are different examples. For more information, you can search for these websites to have more detailed information. And in summary, we studied attention model and how this model works. And then it's a representative application such as image captioning and machine translation and so on. Thank you very much.